In the name of Allah, the most beneficent, the most merciful. Assalamu alaikum. May peace and blessing of Almighty Allah be on all of you. My name is Azim Iqbal, and I am the founder and chair of Pakistan Society of Industrial Engineers, the largest national organization that is solely dedicated to the profession of industrial engineering. We've been operating since 2015, and so far we have a very strong network throughout Pakistan with a lot of students, professionals, and teachers from our community. We've also formed partnerships with international IE organizations, and we try to bring more opportunities for the for professionals in our field. So in the current pandemic scenario, we decided to start an online lecture series, which we entitled as Road to Industry 4.0. This initiative was aimed at building a roadmap strategy for Pakistan's SME sector so that the industry could cope with the current and the post-pandemic scenario. In this regard, today's session, we entitled it as Developing a Quality Approach to Industry 4.0, a remediation to recover from the pandemic crisis. I am very honored and pleased to welcome our distinguished guest speaker today, Dr. Gregory Watson. He's a past president and honorary member of both the International Academy for Quality and the American Society for Quality. He's a past senior vice president and fellow of the Institute of Industrial and Systems Engineers and has received its George L. Smith Award for Excellence in Engineering. Dr. Watson has also been named honorary member of 18 national quality organizations and received over 50 medals and awards, including the prestigious award of ASQ Distinguished Service Medal, Union of Japanese Scientists and Engineers Deming Medal, the European Organization for Quality Border Medal, and the IAQ Founders Medal. He has written 12 books and has published over 600 articles, papers, speeches, and videos in his 50-year career. Dr. Watson last visited Pakistan in 2013, and we had an opportunity to speak with him, to talk to him about the global perspectives of industrial engineering and how Pakistan could come forward as someone in industrial engineering field. And since then, a lot of students have got in touch with him on his various profiles, for example, the LinkedIn profile. And at that, in his profile, he posts webinars on topics related to managing for quality. Dr. Watson holds a doctorate degree in field of industrial engineering from Oklahoma State University and is a registered European engineer in both industrial engineering and systems engineering. So with this introduction, I want to give a very, very warm welcome to Dr. Watson. And so let's begin with the session.
Many thanks, Azim. I appreciate your hospitality. In the name of Allah, the most merciful and the guider of our thinking processes towards true knowledge, I welcome you all. I would like to begin with a quote which I find very motivating to me. I'm 70 years old, and this is a time of very much concern about our lives. And so in the Quran, Allah intends to provide ease for you and does not intend to create hardship. I think many times we can become overwhelmed with all of the uncertainty in life that we're facing because of the pandemic, the economic effects. But also in the Quran, it says, on no soul do we place a burden greater than it can bear. And I think this brings us to the point of what I want to talk to you about. And in these ideas, I think what we see is that we are given certain gifts in life. And the Quran talks about the gifts that we receive. The question is, how do we use them? So I would like to talk about the challenge we have that we face now with this current pandemic, and also the gifts that we've been given in terms of the knowledge we've come to learn through industrial engineering and about quality management, and how do we put these together in the age of technology? Now, technology has always driven the way that we work. And I want to give you a personal example. In 1872, Isaiah Hyatt invented the first injection molding machine to make plastic parts. So that was a long time ago. That was very indicative of the industrial revolution of the last age. In 1946, James Watson Hendley built the first screw injection molding machine. And this was where it was semi-automated with an operator. And it looked something like this. As a matter of fact, I remember this very fondly because in 1968, I had a summer job hand feeding the mixture of plastic pellets and fiberglass. I had to pick up the pellets in one hand, the fiberglass in the other, merge them together in a bowl, put them in there, and then put metal inserts into the machine, hold down two buttons, it came down, and then I had to watch the dial to make sure the temperature was up there. Then there's a timer to hold it at the pressure, and then release it, and then take the part out with my hand, of course, every now and then burning myself because it was hot. Now, if that machine made a bad part, it was my fault because I was part of that process. I was deeply involved in it. I could make the ball wrong. I could get the timing wrong. Maybe it wasn't quite ready to be set up and so forth. But that was what we start seeing back then. Now, what happened in 1983 was a Japanese company, Nisei, built the first all-electric molding machine. And very true to form, what they did was they put various sensors in there and detectors so they could detect the temperature in the mold. They could detect the temperature in the barrel, so where the plastic is flowing. They could detect pressure in the barrel at different points, pressure and temperature at the beginning, middle, and end of the barrel. They could detect the clamping force of the mold, the ejection force from the pins. And they had, of course, a Hewlett-Packard interface bus, HPIB, that could capture all of this information and put it on a computer. Well, in 1984, I was starting my job at Hewlett-Packard. And my second experience in injection molding was an engineering job. It was to design and develop a just-in-time molding process using this new Nisei electronic molding machine and applying the principal single-minute exchange of dies to reduce time. Now, in the old machine, if we had to change a mold, it took about 4 hours. And the challenge was to take up what Shigeo Shingo had said, can you do it in single-digit minutes? And so I was given a couple of young engineers just out of school as a project leader, and these two engineers had never done anything except come out of school. And so what we were doing, they had an open checkbook from Hewlett-Packard. And so the first lesson that we learned was, how do we actually start taking these technological advances and learning them? And the big discovery we had was not one of those indicators that the engineers had digitized into the system was indeed the driver of variation in the parts. So what the variation driver, believe it or not, was the rheology of the plastic. It was the shrink rate. And so if the shrink rate was not well controlled, we couldn't get good parts no matter what we did with all of those issues. So we had to add a manual front end process to actually measure shrink rate in the plastic lots and then control those lots as they came into the machine. We did get the just-in-time cycle time down. We actually got it down to about 7 minutes. And to do that, we had many shortcomings, but what we found out was that 2 hours of that time we spent heating the mold in the machine. So we preheated the mold and put it in hot. And then we had other times that we spent torquing down screws. So rather than having torqued down screws manually, we had pneumatic clamps added to it. We didn't have to readjust the guides. We put automatic guides on the molding machine that matched up to the mold. And by the time we were done, we just moved the hot mold in, and we never changed the resin. So we didn't have to clean out the barrels. And because we did it so fast, it didn't get so that we'd plasticized the resin that was sitting there. So we were able to do that, and we went from running one machine with one part for a day, doing 22 mold changes in a day. And we molded today what we're going to use tomorrow was the motto, so that we would have dimensional stability in the parts we sent to production. That molding center was the first ingredient, actually the enabler of being able to create the very first just-in-time production line at Hewlett-Packard. And that was for the PaintJet, which was the first color inkjet printer. And that was the first manufacturing cell in 1984. It came online in 1985 for production. That was able to make 10,000 printers a month using this just-in-time injection molding center. We only had 8 machines, but we had so much capacity we could do other things too. But we were doing the parts that nobody else could do. So at that point in time, we did screws. Screws are very hard, and all these sorts of different things, like the gears on printers, where the registration has to be so tight in order to get good print quality. And we moved those from metal to this plastic injection molding and reduced cost tremendously in doing that. It was about 10% of the former cost. So technology has a way of driving the way we work. This is one of the examples from my life in terms of what we see. Now, there's a statement that was made by Mark Weiser at the Xerox Palo Alto Research Center. And that's where a lot of the current computer technology that we have actually was generated. So the Palo Alto Research Center, it's also called PARC, and that's where they created the very first Windows icon mouse pointing environment, which Stephen Jobs and Wozniak then integrated into Apple. They created the Ethernet. They created Smalltalk, the first object-oriented language. So, but they had a little problem. They couldn't commercialize any of that. None of it Xerox is known. So we see there's a technology issue, and there's also how do we humanize the technology and make it so it's acceptable to people. But what Mark Weiser said was the most profound technologies are those that disappear. Not disappear because they were bad, but they disappear because they weave themselves into the fabric of everyday life until they are indistinguishable from it. You know, I was talking with Azim before we came on board. We're talking about our fathers and their experience in life. And I was sharing how my father, you know, thought radio was so wonderful. And if I get in a car, we don't even think about radio. It's just there, you know. He was mentioning, you know, his father with television and so forth. And so television, what is that? It's just another screen that we look for communication purposes. And so we start seeing the inventions of the technology have changed our way of looking. And if I look at my life, and I just think back, there's a lot of this magic that occurred. So I told you I was 71. I was born in 1948. But actually, if I take a look at the pace of change that's happened, so if I was born in 1948 in July, that means I was actually conceived in 1947. And in 1947, the transistor was developed. 1948, at the Bell Center, Bell Laboratories of AT&T, they created this bit-byte logic for information technology transfer. 1958, I was in kindergarten, I think, or maybe third or fourth grade, I guess. And the semiconductor circuit was created. 1981, I was now out of university for 11 years, and they created the first personal computer. And then the local area networks in 1987, the internet in 93, and social media in 2004. And so we start seeing that's from this 1980s, there was a major shift towards digital technologies. And it began when the personal computer came out. Now, I remember I was in the US military in the 1970s, and we were doing things called the DARPA net. So the DARPA net was the precursor to the internet. It was had a system called PROFS. And PROFS was the software where the professors would communicate with each other about when can we take control of the computers on the network and bring the 16 computers for the west coast of California together to run some programs or major programs. And so that was the very first email system. Again, 1974 or 75, that came out. And we start seeing these technologies. I remember we had a computer room, and we had an HP 9845 electronic calculator. We had a ray tracing machine from Tektronix 4751 ray tracing display. We had a Wang 2200 VP word processor, all connected on a network through a telephone modem to a satellite net to be able to connect us to this internet system. And we thought that was really cool. And if you took a look at that room today, you would die laughing because it was a safety hazard. Cables running everywhere trying to connect things. You'd trip over the cables, you'd lose your connection, you know. But we thought it was really cool because we could do something nobody else could do. Well, my background is with the American Society for Quality. In 1997, I was the vice president of ASQ for research and technologies. And because I'd had my background in the computer industry and worked in that in the military, and then came out to work at Hewlett Packard and Compaq and Xerox, um, I was made the vice president for research and technology. We had been doing a series of future studies, and in 1998, we did a future study. And in that future study, I was part of that team, and I wrote a series of articles. And this was an article that I wrote in 1998, so that's 22 years ago. And it was called Digital Hammers and Electronic Nails, the Tools of the Next Generation. It began with this quote from Matthew Arnold, a British poet in the first half of the century. And he says, I am wandering between two worlds, one dead and the other powerless yet to be. So that's where we are. We know that the technologies we've had at the past, they've died. But we don't know what the technologies of the future will be. And so all of you, you're taking courses in machine learning, artificial intelligence, I think, I hope. Maybe you're taking courses in Python, and you're taking courses, in R or some of these other advanced languages. And so the question is, how will they be? Well, you're going to get to determine that. And so the challenge that I want to offer you is, how do we deal with all of these technologies, and how do we bring them forward? Now, before I start going into this Industry 4.0, I want to introduce three terms. Each of these define the student-teacher relationship. So they're guru, a sensei, and onshi. Now, you've probably heard of the first two. And so a guru is an Indian term. It's a spiritual teacher or a sage. And it has sort of religious overtones, someone who's reflective. They're not active in the world, but they lack a certain, if you will, pragmatic realism. Now, I don't want to be a guru. Don't call me a guru. I want to be a teacher, because the teacher is something different. And so the idea of a guru is you'll go to them and they'll take a look at their stomach. And quite frankly, I don't want to look at my stomach. And so the sensei, though, is a Japanese term, and it means master or teacher. But it applies to anybody who's a teacher of anything. So it's not a perfectly elevating term. I remember that somebody said that you could be the guru of growing broccoli, or the guru of vanilla bean agriculture, and so that is not necessarily the best or the highest level of being a sensei. The third term is reserved in Japan. It's called onshi. And onshi is a beloved or revered teacher. It's literally, the meaning is an imperial gift, a gift from the emperor, a gift from God. And so what say is, this is very similar to the Arabic term of sheikh. And a sheikh is a learned elder who can teach deep wisdom based on sound experiences. And so as we start talking about this is this wisdom that we can use for life. It's the wisdom that comes from the Quran, for instance. And it comes from this deep place, and we have to figure out, how do we apply that wisdom? So just as if you read the Quran one way, you get one interpretation. If you read another way, you get a very different interpretation. So the question is, what do we do it as we read the book and we become inspired? How do we make that interpretation of those same events that everybody can see? So I want to talk about then this transition we've had in terms of, what do we really mean by Industry 4.0 first? And in particular, how does each of these levels of industry relate to levels of what we can call quality? Well, Industry 1.0 was when humans harnessed water and steam power and created some sort of industrial structure. So before this time, we were basically an agricultural society. Here, the workers would operate with crude machines to gain productivity over this independent craft work, what individual workers were doing. And we see increased output happening because we had the mechanical advantage from those tools. Work was focused on doing a particular task with greater consistency and speed, and the emphasis was actually on things like transportation and moving goods. Now, back in that world, quality 1.0, if we refer to it this way, is assuring by measuring and inspecting each and every important characteristic of the output. So this is where the invention of go, no-go gauges came from. Is it good or is it bad? That's really the question. If it's good, we use it. Emphasis was placed on the volume of production. So can we get more rather than the quality of each item? And so if you were taking a look at the economists of those days, they would say we produced 50,000 tractors. And so the volume, well, they'd make tractors back then. Actually, maybe they did. And so, but the volume that they had was the amount of quality that they had. So that was productivity equaled quality. The inspection didn't focus on cost reduction, eliminating waste, just on getting the job done. And so the idea was units produced is the indicator of productivity. And the conditions of work were not important, how the worker had to do this, just that we got the most out of the worker. And this is, if you will, what we saw before Frederick Taylor wrote his book, The Principles of Scientific Management. Now, Industry 2.0 came about because we now moved from water power to electrical power. And so we could actually have power generated machines. So not just mechanical devices, but also electrico-mechanical devices. And so performance capability came by delivering diversity in applications. We could put these electric motors anywhere in the system, and that they could be distributed, not just because we had water or we had a steam generation system. So we can now take those boats that were big steamboats, if you will, moving on rivers, and we could now move trucks on land because we weren't stuck to that water-based system. We also saw that the scale of automation became much broader because motor size could be varied according to the specific tasks. And the emphasis also then expanded to other mechanical operations that we could have with motors, things like conveyor belts. So in Quality 2.0, we see the emphasis continues to getting the most productivity out of workers and work. And here we had now inspection-based quality. And this was the emphasis on, can we adhere to these systems so we get parts made at the minimal poor level? This is what we call acceptable quality levels. So if you take a look at some of the standards on sampling today, you'll see a characteristic called AQL, acceptable quality level. And if you see AQL 2.5, it means that the acceptable quality level is 2.5% defects. So what that really meant was, if you're going to buy 100% of the parts, you're willing to accept 2.5% scrap and pay for it. Well, that's not a very good economic decision. Financial quality measure is scrap and rework of the output that was not non-conforming. That was the cost of quality in that type of system. The labor-based performance is the measure of productivity. And this is what we had entering into the 1900s. So in the last century that we're looking at, Quality 2.0, Industry 2.0 was what we basically had to saw. And these inspection-based quality systems were what we were seeing. That this is what Frederick Taylor in the Principles of Scientific Management was actually reacting against and saying, can we do something better? Now, at this point in time, the economic model was the model that Adam Smith had in The Wealth of Nations. And Adam Smith said there's a division of labor. There are planners, management, and there are doers, workers. And so they're just those two categories. So he divided labor into those two categories. The workers do the handwork, so they're basically selling their labor time, their capabilities or their energies, and the planners or the managers are doing the thinking components. So what we start seeing is we start looking back in this period. Quality 2.0 was basically from 1890 to 1940. And collectively, we see there were about 12 people that we say, these people were true senseis. They developed fundamental components that became the logical developments of modern quality. So Taylor with his Principles of Scientific Management, Harrington Emerson with his idea of the efficiency of systems, Lillian Gilbreth and Mary Parker Follett with the human component of working in teams, Percy Bridgman, who talked about the logic of how you build systems within boundary conditions and look at things as probability of performance. Schuhart took Bridgman's ideas and turned it into control charts. Fisher used that same principles to create designed experiments and analysis of variance. Harold Dodge and Harry Roaming created sampling tables. Chester Bernard said, this is how we manage this as an executive level, and then how we use these decision processes to drive executive decisions in a company. Egon Pearson in 1933 wrote the very first modern quality standard, British Standard 600, which actually combined the inspection-based system and Schuhart's control charts. And Volodya Weibel created reliability engineering by taking a look at what we see in terms of the fragility of different materials and parts and their designs. And so we had come a long way, but these are all just foundational principles. None of those were, they're now what you'd call settled knowledge, but they're settled knowledge within a small domain. It's not the systems perspective. So along comes Industry 3.0. Industry 3.0 is introducing computer power to gain productivity. And here performance is increased because the productivity of people is being expanded greatly because of ICT, or in information computer technology. And so the gains in human productivity reduce then human participation in the workplace. We don't need as many people because we have thinking machines, smart machines that can do things. So standalone robotic systems begin to replace manual work. And so this is what we're seeing as a transition post-1940. Step by step, the computer was developed in the 1940s, and we start seeing the chips and so forth coming about. But what we see is that in this period, quality becomes a business imperative. We can't keep investing in things gone wrong. We realize that we have to do a better job. The emphasis on meeting customer requirements and satisfying customers, because now what we see is there's a choice. You can choose which brand of things, because there's alternatives you're presented, because there's more of a global marketplace. Continual improvement to gain competitive advantage occurs by reducing quality costs, losses, waste, inefficiency across the whole end-to-end production cycle, supply chain, within the production facility, as well as in distribution processes. And then finally, we see that gains in productivity occur by stabilizing the process at high efficiency, standardizing work, and involving all the workers in activities that create quality. And this is what we see became known as total quality management. So the emphasis that we have at that point in time is on moving things forward. And so this period is from 1945 essentially to 1990. And we see here, now I'm going to call these gentlemen onshi, because we're starting to get things that we can really use. So Eugene Grant created the very first training program on statistical quality control. And that was put into factories in America, and then transitioned into factories in Japan. Dr. Deming talked about statistical methods and how we can use those to improve the way we manage the workforce, and how we actually do the analysis of productive work. Dr. Duran introduced the idea of breakthrough management and the different levels of quality, from quality assurance, quality control, quality improvement, and how we can change both at the worker level, which he called little q, and at the management level, strategic quality, which he called big Q. Karu Ishikawa introduced basic tools for teams to be able to work for problem solving, and also for management, about how they need to focus on customer requirements and customer satisfaction. Shigeru Mizuno was the one who actually defined Plan, Do, Check, Act as the process. So that wasn't Deming. Deming never said Plan, Do, Check, Act. That was Mizuno and the Japanese who were interpreting Deming and trying to make it simple. Because what they had was in 1912, after Frederick Taylor had produced his book, that book was translated into Japanese by a journalist, and they created what was called the Efficiency Society. And they had a process for improvement. So they took the first two steps from Adam Smith, so planners and doers, if you will, managers and workers. And then they had the third step came from Frederick Taylor. The third step was C, the inspectors. And so when Mizuno was came about, he wanted to build on what they had and say, how do we actually do this? So he changed the C to check. And that meant it's not just observing anecdotally, it also means checking measurements, checking against specifications, checking against history, and then do something about it, which was a step that they said we honored Deming because he taught us we had to do something about it. So Mizuno was the one, and he, and along with Ishikawa and Tatsuki Asaka, were the three founders of the Union of Japanese Scientists and Engineers. Armin Feigenbaum wrote a book which popularized this whole concept, total quality control. And then he was actually building on the work of Harrington Emerson, who'd been a consultant to General Electric before that point in time. Philip Crosby elevated the discussion to management and said, there is something you have to worry about. From your level, there should never be any defects. And what that meant is protect the customer from defects on delivery. And so how do you actually bring that into the system became the question. Yoji Akao had two major contributions. One was with Mizuno, creating what we call quality function deployment. And the question here was, how do we first document the quality characteristics that are required by customers? And then how do we deploy those quality characteristics into the products and production processes? So quality function deployment is basically how do we deploy the function of quality characteristics into our system, from the voice of the customer to the voice of the engineer to the voice of the equipment to the voice of the process, so that we actually preserve what the customers are really looking for. The second thing he gave us was he documented the meaning of Hoshin Kanri. So Hoshin Kanri was a system that developed from 1964 until 1991, actually, when Akao's book came out. That was the first case study on what do we really mean by Hoshin Kanri. It developed in 1964, 1965, basically at three companies, as stimulated by Dr. Durand's 1964 lectures in Japan on breakthrough management. And the three companies were Toyota, where they created the very first executive quality steering committee. So Sorichido Toyota, the honorary chairman of Toyota today, was the first quality manager there, and he convened that committee. The second company was Bridgestone, and they had a flag system, and their flag system was to have measurements at the check phase that told management there's something wrong in the process. So they sent semaphores, like flags, like on ships, just to send the signal there's something wrong out there. And the third company was Komatsu. And Komatsu created something called the Presidential Review. And the Presidential Review is when the flag system is telling you something is so wrong, this is what the executive has to do to ensure quality is happening. We also see Yoshio Kondo teaching us about motivation and how motivation is exciting people's, or encouraging people's, stimulating people's desire to work, giving them a circumstance where they have joy of life because of their participation. And that is driven because there's a well-defined job. The job is defined in terms of what the humans can do, and that the workers are encouraged by management. And under those conditions, they can develop self-control. And as they develop self-control, they develop a desire to learn. And as they desire to learn about their process, they want to learn more about the inputs they get and the outputs. And they start then thinking about other people. And they get this desire to understand, how do we get the problems out of those processes? And before you know it, teamwork happens. And that's the teams then that Karu Ishikawa had talked about. And management's job was to encourage that circumstance. Genichi Taguchi came out with an engineering approach to deal with designed experiments that goes beyond fissures. Because what he talked about, was an electrical engineer for Nippon Telephone and Telegraph after the war. And one of the problems that Japan had in the 1950s was to totally redesign their communication systems. When the war ended, World War II ended, less than 10% of the telecommunication systems worked in Japan. And they had to totally rebuild that system. And so they had lots of problems with signal and noise. And so as electrical engineers love signal to noise ratios. So what he did was he created a system where you could deal with the complexities of engineering components and his orthogonal arrays, and produce the output not just about the mean and standard deviation, but also signal to noise ratio. And so he gave you three things to play with to optimize the system. Hitoshi Kume He's not very well known out of Japan, but today he is in charge of the Japanese accreditation uh, organization. And so they accredit all of the people who are doing quality standards and checking in Japan. He's better known for his books, Managing by Quality, and that came out in the late 1980s. And that was the first book where we see quality story. So their step on how you go through actually applying Plan, Do, Check, Act, where it actually merged the steps of that quality story to statistical tools such as ANOVA and regression analysis, which had not been in the original toolkit that Ishikawa had given. So we see that by the 1980s, all of this had come about. And the final element is Dr. Noriaki Kano, who in 1984 created his theory of attractive quality. And this is saying about how we need to think about that relationship with the customer. What is it that they must have? What is it that is a competitive feature? And then what is it that is attractive that says, I really have to have this, I desire to have it. So each of these people now gave us more insight, not just the basic tools, but they took us beyond the basic tools to think about what should we do at a higher level of thinking and operating. So we come to this idea of Industry 4.0 and then Quality 4.0. So Industry 4.0 was actually created, or actually, it's just called codified, in 2011 as a German national initiative. And what it's doing is it's describing the application of computer technology to industrial systems. So how do we gain productivity improvements through the various digitization opportunities we have? And out of this grew the Internet of Things, where we can create various types of devices using the internet to activate or do diagnostics or servicing. The use of big data. So how can we make patterns come out of massive sets of data? Distributed sensor systems. So how do we integrate the observations coming from digital sensors and create more of a systems control network? And so these were all the identification of Industry 4.0. Now, interestingly enough, you notice I stopped Quality 4.0, Industry 3.0 in 1995. The reason I did that was in 1993, the internet came out. And what we started seeing was this massive growth. So Azim was talking about, he was born just at this age, and when he was in kindergarten, I guess, the internet was already popular. I don't know if he was on the internet back then, but I'm sure soon afterwards he probably was. And so we start seeing, so his radio system for my grandfather was the internet. His father's radio was a television, and your radios now are the social media that came out in the 2008 timeframe or 2004. By 2008, digital technology had already surpassed all of the analog technologies we need. That's an interesting point. Now you can go and justify this. I've got other papers and speeches I've talked about that. But this is interesting. So by 2011, the Germans were actually a little bit late on the digital trends. I did my first work on artificial intelligence in the 1970s and was looking at network systems, embedded software. We had sub-1 micron technologies in the military by the late 1970s. We had artificial intelligence algorithms doing sensor processing from distributed detection systems. But that was the military. That was not something you could afford to put into a commercial application. But now we're about 40 years, 50 years later, and we can afford to do those things. Because those digital sensors now, I can go to Alibaba and buy them for less than €1. And so what was 10 years ago, 10,000 euros, what was back when I was growing up, massively incomprehensible millions of euros, it now has become to the point where we can actually do those things in a reasonable way. And so what we start seeing is Industry 4.0 is this process. So it's integrating cyber physical interfaces to automate working environments. The systems have to deal in this end-to-end automated process. And humans are only serving in positions where human judgment has not been capable of automation, or if a human interaction, the need for touch or empathy, cannot be simulated by virtual reality or response systems. And I'm going to put in that yet, because that is a move. But the machines learn to learn. And I think this is this ingredient, adaptive learning processes come about. So we're going to talk about this, and then how does Quality 4.0 change as a result of that? Well, we see that this digitization is a critical ingredient in this process of optimization, because we get signal feedback, process adjustment, adaptive learning, and these are allowing the systems of production to change using self-induced corrections. So they can observe the signals, see what's happening, and make their own choices about how to manage the system to create better quality output in the future. Quality is shifting from control of humans in the process to the control of the human designing the process. So the process by which the adaptation of the machine will learn how to learn, and the machine will self-regulate how to manage the system and the productivity quality of the output. And so there's a major shift happening. And so if we think about this, we start seeing that the quality thought leaders post-1990, well, we don't really know who they are. They might be you guys, okay? You know, history says that they need 25 to 30 years to decide the value of past contributions. And what I see is, in my interpretation, there was a major pivot point that occurred just before Azim was born. And so this created a whole new world for him as this baby in diapers to come out and saying, what am I going to do with my life? So there are four components that changed quality in the year 1987. So one was the Malcolm Baldrige Quality Award. And what that did was it gave a set of items to address, specific areas that need to be considered, questions that management needs to ask themselves about how do we improve the quality inquiries, how do we improve business performance by making more focused quality inquiries. And that's what happened with the Baldrige Award. It's not comprehensive, it's not complete, it doesn't tell you what methodologies, but it does give you a good set of questions to ask. 1987, ISO 9000 was issued as a generic quality management system. Now, ISO 9000 is the third generation of the standard that Ian Pearson started with British Standard 600. Then came British Standard 5750, which was then translated into ISO 9000. Now, what most people don't realize is that there had been standards before ISO 9000 that did this, but in 1983, when Ronald Reagan was president of the United States, he canceled Military Standard 9858, which had been the standard for quality, which was the quality inspection and control standard that the military used, but was also used in aviation and aerospace. And so all contracts that were issued were saying you have to deliver quality according to that particular standard. And as we look at these things, we start seeing back then that Reagan believes in deregulating business. So 1 second, I'm going to get a little coffee here. And because he deregulated business, he got rid of standards that were considered to be onerous. It's too difficult for industry to keep them up. Well, sure enough, what happens after he canceled that, nobody then knew how do we evaluate quality in automotive industries, aerospace industries, military, the national space, NASA, and so forth. And so there became a very large feedback loop where each of the different components saying, if we don't have a standard, we have to create our own. And pretty soon the craziness of that got to everybody and said, we have to have a way to have a system that's integrated. And therefore ISO came up with the adaptation of BS 5750 to become ISO 1987 version. Now, what we see about this is it gives us a checklist of items to address about what are necessary ingredients of a quality management system. But ISO 9000 does not tell us what particular practices to put in place. It doesn't say you have a better documentation system if you have a relational database with pointers and indicators embedded in the system, so you know how to cross-reference from the customer requirements all the way through specifications. Oh, that probably is a best practice. It doesn't tell you that. It doesn't tell you that you should use statistical quality control methods to monitor production processes and have feedback loops so you can, automatically correct it and not make garbage. Well, that is a best practice. It doesn't tell you that. It gives you general guidelines. So it says use appropriate statistics. So it's still not the comprehensive system for quality. 1987, the third ingredient, Motorola came out and introduced Six Sigma. And what they said about Six Sigma was all of their suppliers had to use Six Sigma to improve the quality of their parts. Now, interesting, Motorola had not done Six Sigma yet, but they had the audacity to tell their suppliers, you have to do it, even though we haven't done it yet. And interestingly enough, the first company to do it was actually one of Motorola's customers, Unisys, who made that as a requirement for continued operation of work with Motorola to continue buying chips from them. And so Motorola helped Unisys implement Six Sigma in 1990 or 88. And it wasn't until 1991 that George Fisher, then the chairman of Motorola, announced, hey, we finally got this Six Sigma thing done. And we're ending that program as management attention. It's now part of daily management for us. So Six Sigma started growing, it expanded and so forth, and now we see that as a major ingredient. What Six Sigma did, though, was it gave us a methodology, a structured plan, do, check, act approach, which it calls DMAIC. The Japanese don't like that because they said you didn't take a scientific approach. You should have used plan, do, check, act, because this is how the whole system linked into what we have done in 50 years of scientific investigation. But we Americans, we're commercial beasts. And so what Michael Harry did say, no, I can make more money if I create my own and make you feel, come and worship me. He created a stupid measure, Six Sigma. Six Sigma is a horrible measure. I don't even teach it. It's obsolete and has been for 20 years because it's totally valueless. People do not understand Sigma as a measurement system in management. Sigma changes every time customers change their requirements. There is no standard customer to customer or industry to industry way of dealing with it. And so it's perfectly adequate to deal with process capability because there is a relationship between process capability and Sigma, but I don't need this artificiality. It's just a headache. And so do away with this. I'm actually writing an article now called Planning the Abandonment of Six Sigma. And I'm so tired of people from the outside saying Six Sigma is stupid. Of course it's a stupid measure. We've known that all along. Nobody's trying to defend it. But then they try and paint the whole lessons learned from the Six Sigma process as being stupid. And you can't go back to the old way of doing things. You have to figure out what's the best way to do things. And that's the challenge we see in the years post-1987. So I see now that we're in the seventh and perhaps going to the eighth generation of Six Sigma thinking. And somewhere around generation 5, Six Sigma dropped out as a measure. So we shouldn't keep focusing on that because it is a totally ridiculous measure. Now, one other thing happened in 1987, and I think this took the icing on the cake. There was a study that had started by General Electric on its cross-industry quality network, 16 companies. And what they did was they studied the divisions on those companies and their head-to-head competition. And they evaluated what was the perceived quality level, what was the market share, and what was the return on profit or return on investment for R&D projects. And what they saw was that R&D investment was the greatest when market share was maximized and customer perceived quality level was higher than the competition. At that point in time, the profitability was twice what it was when neither of those conditions was maximized. And so they declared in chapter 6, the customer is king. Now, that book, The Profit Impact of Market Strategy, was published in 1987. The study was actually published to the companies that did it. It was conducted by the Wharton Graduate School of Management, an excellent school on finance and quantitative methods. The group of professors that did that came out and created the Strategic Planning Institute, SPI, who then did this. And two of the professors, Bradley Gale and the other guy's last name was Buzzell, I can't remember his first name, but they created this book, The Profit Impact of Market Strategy, published in 1987. That took executive world as a storm because now they had content to add to the Baldrige questions. And so they could say, okay, well, what do we do for the customer? And they started getting the idea. So they were actually evaluating the outputs of their performance for the Baldrige Award, and it started making more sense. So Quality 4.0, what do we mean by this? Well, the term has only been around since 2017. So in 2017, I gave a speech. There was the first ASQ conference in Europe. It was in Berlin. And I defined Quality 4.0 this way. I said it's the application of digital technologies to productive systems to gain profound knowledge of their operations so they may be optimized for performance in real time. So there's sort of three things happening there. Digital technologies applied to productive systems with the purpose of gaining profound knowledge to optimize performance. So those are the things that we start seeing that are happening there. So what do we mean by this? Well, we start talking about digital technology, and we see there's really 6 different components of digital technology. There's this, first is detection and data capture. These are the distributed sensors we have out there. So they are actually noticing and observing what's going on. Now, they haven't made sense out of it yet. So this is about situational awareness. And then I have to get it from the point of detection observation to another point where it can be stored. So that's data transmission, things like wireless technology or Internet of Things. And then we have to have some way of recording this, because if we don't record it, we don't know what happened in history. So we record it and store it. So this is cloud computing, it's optical storage systems. And then we have to have sorting and processing so that we can understand what does it really mean. So that's big data, it's machine language, if you will. So we can have some sort of system that tells us what's going on. Once we have situational awareness, we can start creating a scientific approach to using that data. And here what we see is data modeling and start taking a look. So maybe something like a neural network so that we can see how things are related to each other. And then we can start doing data application. So this is where we can have optimization systems, feedback loops, computer numerically controlled systems, 3D printing and so forth, that make sense and actually do something with the digital technologies. So this is the structure I actually spoke about at the American Society for Quality's first virtual conference on the 5th of May. And if you join my LinkedIn, you'll see under posts that presentation that led up to this is there. Now, productive systems have 4 different components. So first, there is the technology. This is the robots, it's the communication systems, and it's also the software that supports those. The second component is the human social system. Now we see that there's 2 ingredients. This is the people working in the factory, and it's the people designing the system. What we see now is as the technical systems become smarter and smarter, we start seeing a reduction of the people in the factory. So one of my client firms here is Carlsberg Brewing. They make beer, and they're located about 50 miles from my house, roughly about 80 kilometers, and they have a distribution center there. And in the distribution center, there used to be about 50 or so employees back about 10 years ago, and today there's one employee running a very large warehouse that's totally automated system. Now, this reminds me of an old joke from Warren Bennis. In the 1980s, as automation was becoming very important, people saying, we're going to have the factory of the future. And many people studied factory of the futures. They gave seminars on the factory of the future. And Warren Bennis made the comment that the factory of the future will have 2 employees, a man and a dog. He says, the man will be there to feed the dog will be there to make sure the man doesn't touch anything. And so this is this human social system we're moving to. And so I asked the people at this Carlsberg warehouse, what did you do with the dog? I felt so sorry for this poor dog that no longer was in work, but I was concerned because they need to bring the dog back to make sure the man doesn't change the systems. Now, lest you think that that's a one-off, there's a whole Chinese company, ZPMC, that's actually creating port systems. So in the Chinese Belt and Road system, the port is managing the offloading of all the container ships. that their ports only have a control center. Offloading is robotics, moving on to automatically guided vehicle, who then take it someplace where another crane puts it on an automatically guided truck to take it to its destination. And that is a reality today. So a third ingredient of a productive system is the management system. So this is this component. How do we actually manage in that system? So this is the planning and control system. It's how we do scheduling. It's the communication system. Not only how do we understand requirements from customers, but how do we get feedback from customers about how well we did? How do we advertise what we did? And it's also the data collection system for what are we going to do when we design this system to come back together. So it's about new product development. And so those are all management systems that have to exist. And finally, we see there's a number of cultural values. And the cultural values are another component of those cultures of the productive system. And this changes because there are many different cultural or moral codes by which we operate. So at the beginning, we begin our presentation by giving thanks to Allah for the many kindnesses and benefits that we've got. We go to another culture, they wouldn't do that. In China, they think about Confucius and the wisdom of Confucius and how it addresses them today. So in Japan, they may go back and think about Taiichi Ono, or something like this, or actually Miyamoto Musashi, what happened in the art of war. So every culture has a different, if you will, construct about how it builds. And we see there's a culture of industrial engineering. There's a culture of production applications. There's a culture of marketing. So we have disciplinary culture. We have national culture. We have tribal culture. And so I don't have to tell you guys in Pakistan, you have some of these tribes, you know what I mean. So every tribe has their own unifying bond and things that they bring them together. And so we start seeing there's more diversity on the cultural side than there is on the technology side. So how do we adapt this in the human environment is the social system and also the cultural system, and how do we build on that? So those are four components we have to think about as we build a productive system. And how will that apply when we bring it into human society? When we talk about profound knowledge, this goes back to the four components that were suggested by Dr. Deming in his book, The New Economics, that was published in 1993 and then revised in 1994. And his system of profound knowledge had four ingredients. I'm changing the words. I did my doctoral dissertation on this, so I have the right. and so he called the first appreciation of a system. I think you have to do more than have appreciation. You really have to understand the system perspective. You have to figure out how we define knowledge from that end-to-end viewpoint. And then he said theory of knowledge. Well, theory is no good without practice. One of my favorite schools is MIT, and the motto is mind and hand. So if you get the theory right, you can't put it in your hand, it's no use, okay? So we have to manage the knowledge domain so we can do something with it. He said the third item was variation. And actually what we don't want is variation, we want predictive analytics. And that is understand the variation so we can make a prediction how to use it in the future. Because then I can actually create the feedback loops. And then he talked about psychology, and I think about, well, I don't want to sit on a couch and be judged by somebody who's psychologist and telling me all about my problems. It's really about human understanding. What does it take to motivate people? How do we get people excited? How do we persuade them that this is something that they need to be involved in, dedicating their life energy into actually creating this new state for the benefit of all of us as a social system? Now, when we start thinking about what we do with these things, I want to put in a couple of contexts. So the first context came out from the United States in the National Academy of Engineers in 2008. And they called these the grand engineering challenges of the 21st century. It was their to-do list of what engineers need to dedicate themselves to do to save the world. Now, this is all engineers. It's not just industrial engineers or quality engineers. And so what I look at this is the first part of this, it was basically the role of science and engineering. So make solar energy affordable, provide energy from fusion, develop carbon sequestration methods, manage the nitrogen cycle, provide access to clean water. And so we start seeing, well, all of those are very advanced engineering approaches or scientific approaches that need to be dedicated. But the last two, advanced personalized learning. What are we doing today? Look at what happened in the last 4 months. We're getting more personalized learning, but we are still coping with how do we deal with that and engineer the tools for scientific discoveries. And that's what we're doing with this Quality 4.0. How do we actually apply those methods in a new way? So Industry 4.0, Quality 4.0, these are the opportunity to advance quality. And that came out of this 2008 study of the National Academy of Engineers. Now, you might remember 2008 was the year I said that the digital transition was completed. Analog systems have basically been replaced by digitized systems throughout the world. That doesn't mean that they're integrated into everything, but all of the technology had been developed at that point in time. It's developed so well now that every 2 years, we are doubling the amount of information that's available on the internet. So every 2 years now, the internet data is doubling. And so that's like a petabyte of data. Now, that's not when the cat bites my hand, okay? A petabyte is a lot of data. So think of that as a high stack of terabytes of data, okay? Now, another challenge comes out from the United Nations. And they have issued their sustainable development goals, and there are 17 of these. And we look at these and we start seeing these are challenges to the whole socio-technical system. Many of these deal with this cultural component, and we start seeing the cultural component varies across many places of society. And so what some people do is they say, well, wait a minute, we don't really follow some of these cultural components. And they go against some of the moral components of our local culture. And so the question is, if these are perceived as generic cultural challenges for the social technical system of humanity, how do we actually attack those problems as a global system to start making improvements happen? And I think this is a very big challenge because many of these, when we take them into local cultures, they don't operate the way that they do at the global level. So the challenge is, how do we build this? And we start realizing that what we are in is increasingly becoming seen as a socio-technical system, that the work is becoming more complex. So in 1997, Dr. Duran predicted that the 21st century would be the century of quality. It's 2020, I'm still waiting for that to happen. In 2003, I believe it was, or no, 1998, excuse me, Stephen Hawking, the British physicist who just passed away, who was talking about the Big Bang and black holes and all these sorts of things. He made the observation that the 21st century will be the century of complexity. So I talked about this, again, you'll see a speech on this that I did in February this last year. But basically what's happening is we have a social system, people working in organizations. We have a technical system with technologies and the activities or the work that we do. And we see their interactions between people and technologies, organizations and activities, and all of these cross systems. So the hardware and software technology, these are the physical systems we use to evolve the change in our organizations and organizing ourselves to do the work so we can interact with each other in a more effective way. And so the idea is we have to reduce complexity in order to have an innovative solution. So we have to move from complexity to simplicity. So technical complexity, we do this by moving from disorder, so having all of those systems that I had in the 1970s in the computer rooms with cables and all the disjointed systems where we had to build a lot of interfaces, we have now process engineering. We do that by design. On the other side, social complexity, we have to move into order by having better systems thinking. That's about the heuristics, or how are we going to actually create a better design system in which human beings work. So the principle is we need to design order by structuring the disorder. I love to say that we work in a world of dirty data and messy processes. The data doesn't tell us anything right away, and the process is such a mess. Our job is to understand what is worthwhile out of the data that will give us the knowledge to clean up the mess in our processes. So the challenge is, the burning question becomes for us as engineers, how do we implement the technical dimensions of digitization with the human dimensions of society? So this is the challenge that I want us to turn to right now. Now, we see that quality management does give us some guidance. And I like this photograph because it's talking about the future. It's talking about the balloons in the air, which symbolizes happiness, and some young girl looking forward to dreams. But defining quality in a way that allows us to understand, what does a systematic application actually mean? And so that means we're going to create the magic of and. So we want to concurrently deliver these things. Global well-being, so we all are having viable, worthwhile lives, and environmental security, so we're not destroying the world to get this, and equitable prosperity, so we can all live to some basic standard of living for the benefit of human happiness. I go back to the quote from the Quran. What does Allah ask? You know, you won't be able to bear things that you cannot bear, to create something of life of ease, not of hardship. And that's the fundamental that we're looking at. So I then turned to my early days in university, and I like to confess this particularly to engineering students. Yes, I am an engineer. Okay, but my undergraduate degree is in philosophy. Okay, with a minor in chemical engineering. But you know, that was the 1960s. It was a rebellious age. And I didn't like the exam that my professor of organic chemistry had given, because he gave what I considered a philosophical exam. And he gave us essay questions. And I said, no, that's not the type of test I want. I want to understand covalent bonding, test me on carbon chains. You know, what are the different things? How do I deal with transitioning, you know, gaseous systems into liquid systems, and really interesting stuff. And he says, that's the exam I gave you. If you don't like it, you don't have to take it. And so I signed my name on it and turned in a blank piece of paper. I went to the dean and I complained about the professor. And I said, you know, if I really wanted to write essay questions, I would have become a philosophy major. And the dean made a joke and he said, oh, is that what you want to do? Change your major to philosophy? And challenged by an authority figure, I said, yes. So I changed my major to philosophy. And then I specialized in scientific philosophy, the logic. I read Aristotle. I read all of the different logical things. I actually found out in my first course on logic, I knew more than the professor, who was actually professor of religion. So I ended up teaching the course and then the follow-on course on symbolic logic, because I'd had math through advanced calculus and I had no questions about how logic worked. And I'd also worked on computers because we had computers, and that's all logic. And so I got a graduate fellowship in analytic philosophy to do a doctorate after this. Well, my military career, I didn't have any choice about this. I was conscripted into the military, and so that then changed everything and turned me back into an engineer again. So I want to come up with a transcendental definition of quality. And this is a definition everyone can accept. And so I remember, you know, Einstein was pursuing the question of the unified field of science. What is that unified field theory? And this is a big question over 120 years ago. And so I came up with, after about 10 years of research, literally thousands of pages of writing to try to come up with a unified theory of the quality field. And so I came up with this in 2016. I said, quality is the relentless pursuit of goodness. We never give up. We always look for the good, coupled tightly with the persistent avoidance of badness. So if I get goodness and I still have badness, that's not quality. If I have, I avoided badness, but I still don't have goodness, that's not quality. I have to have the two together. And so what we're saying in practical terms is we're doing the right things right and avoiding the wrong things. Now, that doesn't help me to define how do I actually do this in a real world. This is philosophy. It's about how we structure our ideas or thinking patterns. And what we have to do is take that transcendental definition and then make it practical. So if I'm dealing with products and I have a particular industry or company, I have to have a product quality definition. If I'm in a service industry where I'm providing services to people or support for productive systems, I have to have a service quality definition. If I'm working in a process where what we're doing is we're thinking about the linkages of how to produce products or services or deliver them, I have to have a process quality definition. So the question is, in each of those, how will we operationalize this definition? How will you define what is good and what is bad, what we should seek and what we should avoid? And so that then becomes a structure that we can use to think about what will we actually do and how do we apply this in a real world? Well, that's the job of engineers. And I think of this as a job of what can be called managerial engineering, or as I wrote in my 1994 book, business systems engineering, where we should engineer our business as a system. And as an industrial engineer, I see that is a very large part of what we're doing. And so then the question is, how do we do this? Well, engineers work on evidence, evidence-based profound knowledge. And this is what the outcome we'd like to have is, how do we actually find evidence that we are doing the things we need to do? So first, we should clearly define the priority objectives that we want to achieve. What is it that we need to be getting? What's the purpose? Why am I here? What are we doing together? We should then establish what is an accountable measure for those objectives. Not just a report measure that we say after the fact, but who in the process can be held accountable for the performance of delivering that particular purpose or the priority objectives. And then we have to assign responsibility for that particular work and the improvement projects to get us to achievement of those objectives. And then we have to investigate the system of the interrelated process to find out where and why variation from this current or the desired state exists. And then what are the things that are the system of causes that constrain the outcome so we don't get to achieve those objectives. ISO 9000, 35,000, I think it is, just define risk as anything that stands in our way from achieving the objectives of the system. And so that's exactly what we're looking at. We've created risk because there's a constraint. That's something that's creating a friction or a lag or a leak in the system. So we don't get this. And that leads to losses because we have waste and inefficiency. We also have to engage workers in mutual participation to develop solutions and develop or build enthusiasm for the future. So enthusiasm, interesting word, comes from the Greek, entheos, and it means to be filled with the Spirit, to be excited. One of the reasons I love to talk to young people is they get excited. People my age, oops, not necessarily so. Okay, so we want people who are enthusiastic about getting to the end. We also see that there is an approach to how can we develop this. Now, this was a model I put in my 1994 Business Systems Engineering book. And I'm in the process now. I'm going to be upgrading this and we'll be putting a series. Actually, I'm looking at developing about 14 books that are going to get sold on Amazon. And I've just got fed up with all of the publishers, and I thought I'll just go direct to the cycles. To the market. And so if we talk about PDCA as the basic model for change, what we have to realize is in the 1990s, Japan came up with another model also that integrates with it called SDCA, Standardized Do Check Act. And Duran said, if you don't have a standard, you can't improve. And so what I did was I took a look and I said, there's 4 levels of change that we have to have. And at the 4th level, we're ready to do optimization. But the first time, we don't do PDCA, we do SDCA. So the first time is we examine what it is we're doing. Some people call this a Gemba walk. And the purpose of that is to build understanding. And so as we understand the system, we can understand what is the good, what is the bad, and where do we need to make improvements. But before we make changes, we have to then document that system. And that means to get agreement among everybody in that system so we understand what needs to be done differently across all of the different steps in that system. The third time we ratchet that cycle, we now can simplify the system because we can make the improvements. This is about the waste elimination. This is the 3S's of 5S. So it's understanding the knowledge of the system. What are we doing? It's sorting and searching out what we have to deal with. And then it's putting that into a state of readiness and cleanliness. So we've simplified the system by eliminating the waste. And once we've done that, now we can move from the daily management system into strategic management. And the purpose of strategic management is to optimize the system. So we have to go through cycles of learning before we actually build the productive system. And this is an important thing because I don't want to automate systems that are not operationally productive. Yeah, if I take a system that is operating at 50% efficiency and I buy another one, that means I have two systems giving me 100% efficiency from the singular system. If I take the one system that's 50%, move it up to 50% and buy it, then instead of one 100% system for the cost of two, I have a 200% system for the cost of two. So we get twice as much productivity if we work on getting all of the waste out of the system before we move to the decisions about digitization and process automation. And a practical example here, two of them I have. One is in the 1980s, the US automotive industry invested about 50 billion US dollars on robotics and automation. And they did that in the 1980s to increase the productivity of the US automotive system. How much productivity gain did they get for that investment in the decade of the 80s? The answer is none. So 50 billion invested, nothing gained. Why? Because they were automating processes that still had waste in them. So they made waste better, faster, cleaner, but they didn't get rid of the waste before they went to automation. So if we applied this principle, understand, document, simplify, then optimize the system, then we wouldn't have had that problem. The second illustration is what many people do with enterprise resource software, like SAP. And I remember taking a look at many systems where they had gone through and they said, oh, we're going to put SAP in. And what they did was they put SAP in as managing their old enterprise that had all of the waste and all of the bad processes embedded in it. And when they did the SAP, they said, we can't run our system. Why? Because now it became clear what was wrong with the system. What they should have done was first understood, documented, simplified, removed the waste, and then implemented the SAP. So one of the companies that did it right was Nokia Mobile Phones. They didn't implement all of SAP. They did the R3 finance modules only, 1994, and they took 5 years to put the whole system together as they were using Six Sigma and other methods to figure out their processes, how to make the processes work, streamlining the R&D process. So they went from 36 months new product development time in 1993 to 9 months in 1999. And now it's worthy of automating because now you can actually see what the control mechanisms need to be. So what I see is that there's 3 major challenge areas for you all as industrial engineers in the future. And so the first is we should implement the technologies that will streamline productive systems and improve quality in products, services, and processes while we keep the costs low. Now I'm going to come back and talk about each of these with one PowerPoint slide on each one. Second, we should reestablish unreliable supply chains. Now this is something that we just got broken. The global supply chains now are broken. So how do we create them or recreate them so that they become robust and risk resilient? So they can operate efficiently, effectively, and economically by increasing the level of self-regulated performance capabilities. How do we get this system to use knowledge so that it can deal with these things in a better way? And finally, how do we design a reimagined workplace of administrative activities to take advantage of what's happening now with this, using this third-party work. So there'll be more something as a service types of industries, or self-service, combination with a virtual structure of the workplace, or remote meetings that reduce the overhead burden on organizations. So we see administrative functions will change. Let's take a look at each of these. So we're adapting advanced productive technology. We see that there's a lot of motion systems. So we see robotics, AGVs, conveyor belts, intelligence systems, data historians, blockchain, neural networks, learning algorithms, machine learning, AI, pattern recognition. So many things in these areas that we can bring into new technology applications. We see data warehousing and analytical systems, so wireless networks, digital electronic recorders, data logs, big data, automated process mapping like Celanese, optical cloud storage systems. And we also see computer-aided production systems at the end, the numerically controlled manufacturing cells, CNC, 3D printers, programmable logic controllers, PLCs, remote diagnostics, the Internet of Things, connecting distributed systems. So there's lots of technology. And I think now we're doing a reasonable job of starting to address those in terms of industrial engineering, that we're starting to see all of these components. How do they come together? But this is just one application. If we start talking about re-engineering a robust, resilient supply chain, we get something different. How do we drive this procurement make versus buy decisions based on total cost of ownership? And what we see is that our accounting systems actually hide many of the proper decisions we should make. The total cost of ownership says, don't just do something in low-cost country, include the cost of warranty, scrap-free work, expediting cost, field engineering, transportation, the additional inventory we have across the whole system at raw as well as finished goods, or waiting for customers to accept an order or to accept a delivery. So we also have to see, do we have procurement partners who are able to deliver technical contributions to our design and our production processes? If we go to the lowest cost company, what we might find is they don't really have engineering capability. So they can't support the competence of our engineers, and we have to then send our engineers to do work that they should be able to do. So do these companies that are supposed preferred suppliers, do they have production engineers? Do they have material science? Do they have design and tooling engineers? And this isn't on most of the checklists that we use for evaluating the technical competence of somebody who could be a preferred supplier. And finally, we start seeing we should focus selection criteria on responsiveness of suppliers at the product design, as well as flexibility in manufacturing to accept order changes. So we need suppliers who are financially stable and can manage the complexity of this uncertain order stream, because it's uncertain in our business due to changes in the market or changes in risk. So can the customers actually grow with us as we start seeing those changes happen? And then we start seeing this question of reimagining management for remote thinking. Well, we see that travel's restricted, remote work, this is probably here to stay. You know, one of the easiest things for management to control are the discretionary expenses about training and travel. And so as they start realizing that they're cutting those back, there's a benefit from people not traveling. Now, how do we have something I called collaborative analytics? So early in my doctoral, I wrote a paper on this. I never published it, but I believe I need to. It was called Collaborative Analytics, and it's about how will we manage analytics in the future, where I'm going to be now working with a team of young engineers in Pakistan, for instance, and maybe they're going to be bonded to a couple of guys from China who understand something, and maybe there's somebody in Japan or the United States, and we bring that term together and we're going to work on a problem together. Well, our face-to-face meeting time is very low. So how do we actually do that in a world of a virtual team? That's going to be a major change. Now, I remember virtual teamwork. We thought there was a very big advantage in when I wrote my book, Business Systems Engineering. The reason I had to rewrite it is the technology I wrote it on, 1994, is very old. I mean, there were 5,000 databases in the world at that time. And I thought I was pretty good because I had access to all of them. And so I talked about RBase 5000. You know this system. Yeah, it's very popular software, right? You've never heard of it. And so it started talking about digital pointers that we could have. Well, this is nothing new. All systems are working on digital pointers systems like this. And so it also had ability to port this documents out of Lotus Notes, from Lotus Notes into RBase, so we could play with the data. And I could then create a shared document in Lotus Notes so we could all work on the same document, but only one of us could check it out at a time to change it because it couldn't do automated change control. And there were no blogs, but I could actually create a pseudo blog by having an email address we all share and write messages to it. And so all the workarounds, but today, all of those systems exist. So we can actually create a collaborative analytic environment. We also see that one of the things I really dislike about this environment, one of the reasons I held back from being a big person involved with wide use of email, wide use of internet systems, is because we have to improve the ways we communicate and share information. Cybersecurity, digital protection becomes increasingly important. I've had my systems attacked by worms, by hackers, and so forth. And it's frustrating when we start seeing our data being lost or that we have to go back and restructure a computer. And so we start seeing that blockchain technology is going to be required to develop secure communication channels. And this is going to be a fundamental building ingredient of the next generation. And I think when I look at my grandchildren, augmented reality becomes really cool because they can move it out of the gaming world and moving into a mechanism to make meetings more realistic. So this is sort of one version, very entry-level version of augmented reality. You can see my face, I'm sorry, but you can understand that, you know, we're having a conversation, albeit sort of one way, but you're going to get the question soon. And so we also start seeing that we can do this with cartoon characters. We can start animating, and it's a one-way communication. But how about when we create a hologram of me, and I come into your room, and maybe we're in that hotel, Azim, that we were in back in 2013, and I get posted there, and you can see a holographic figure. You can ask questions. I can see you as a holographic audience, and the next thing you know, we're having what feels like a real-world conversation in an augmented reality world. So in order to manage those sorts of data streams and diagnostic software, we have to have all of those systems. Today, that receiver for that hologram costs about 100,000 euros. And there has to be a transmission site and a receiving site. And the cheap end is the 100,000, that's the receiving site. If you're going to transmit back to me, we're talking about a 2 million hardware investment for both ends of the system. Well, I think in 5 years, that will come down. You'll be looking at my living room, and instead of looking at my face, you'll be able to look out across the room, and you'll see a totally different environment because you'll have 360 views, not because I've just moved my computer around so you can see how I live. So that window, by the way, is my window to the world now that I'm stuck here. So I get to see, you know, the sunsets, sunrises, and so forth coming up. It's not a particularly gorgeous day today, but this augmented reality will start becoming richer and richer as time goes on. So how do we adapt to this engineering challenge personally? So I want to now turn from the challenges we have collectively as engineers to what will you do about this? So we're going to start seeing that self-directed management systems are going to become a standard, if you will. So how do we self-regulate performance of our work? That's going to become part of the new normal. If I'm a distributed worker, I have to have some sort of control over my life. So if I have obligations, I have to meet those deadlines. When we come together in this virtual world, we all have to be prepared. And we have to have different decision rights and different control of resources to make sure that we can actually make the most sense out of our process management. We also see workers will become more responsible to exercise the self-control. and to manage their own career development and education. My daughter is I have to think, she's 26 now. And so she hasn't been able to go to work. And what she's been doing is she's been creating now education programs for herself. So she's gone through Coursera and Udemy and other certification programs. And she's got 3 or 4 now new lines on her CV because she had the time to do it. And so this is, you know, she comes out of this as somebody who is more valuable as an employee as a result. So we have to see that we will see these broader varieties of learning will become new learning modes. Software robots will go out and teach. Agent technologies will be used to create a tutor or a coach or a mentor in a new adaptive learning environment, customized on results. I have a crazy idea that I will live on past my lifetime as an internet meme who's a tutor for people on quality. So, God knows I don't want to have to do it, but can you imagine what it would be like if you could go back and pull out from the different people who made those contributions as onshis to ask them, hey, Dr. Kano, what did you mean by attractive quality? You know, how did that relate to Hertzberg's hygiene motivation theory? And then how did it apply on the psychology of Maslow's hierarchy of needs? What's the interrelationship between all of those? It's a good essay question, by the way. So you don't take my course on customer motivation. And then we start thinking virtual teams will be managed through project management systems that guide us through projects, problem solving, managing change, documenting system standards, digital nails, electronic hammers. And what we start seeing is that quality of human life obliges our collaboration. And I want to return to someone who's had a major influence on my life and thinking. That's Dr. Karu Ishikawa from Japan. And he made major emphases. He made total change in his life after World War II, where he could no longer work in production because of the constraints of the war. And he had to change and go into university professor and becoming a quality consultant. And what he saw as as a result of that personal experience in his life is that quality had to be focused on humanity. He passed away in 1989. And before he passed away, he gave what he called his benediction. And he said that his wish was that quality and related activities be spread everywhere in the world, that quality all over the world be improved, that costs be lowered, that productivity be increased, that raw materials and energy be saved, and that people all over the world be happy, and that the world prosper and be peaceful. That means comprehensive, inclusive action that results in good quality of life for all of society. And what that means is we're going to be persistently pursuing good and relentlessly avoiding the bad. So that's the end of the conversations. I see I've gone an hour and a half in terms of lecture. I don't know if you're tired or not yet, but what I'm going to do is stop the screen sharing, and so you'll see my face more real world, and ask Azim, have some questions come in, and do you have any questions, or how would you like to take it from here?
All right. So first of all, thank you so much. It was such an enlightening session. Specifically, your experience. I was actually, you know, I didn't thought, but you mentioned that in 1970s you worked on the artificial intelligence.
Yes.
So that's
we had
really, mm-hmm.
we had a system. We were looking for Russian submarines. We had sound systems, and we collected data, and there are about 250 different variables about sound propagation through water. And we were using then an AI screening system to be able to develop pattern recognition, frequency matching. We were sorting through the massive data with a Kalman filter application to search out for signal to noise.
Okay.
We had a discrete Fourier transform reducing the noise level so we could enhance the signals.
That's
and then
great.
doing a frequency match to particular Soviet submarines.
So I actually went on after doing my bachelor's in industrial into master's in computer science, particularly for this reason that I wanted to get into this technology and learning about this stuff. And my master's thesis was in application of Kalman filtering and nonlinear mechanics.
Ah,
So
well, I still remember there was a very new book at the time by a man named Gelb, Applied Optimal Estimation. You may know the book.
yes,
And at one point in time, I had to actually write a program based on his system on Kalman filtering. And it had to go into a handheld calculator, an HP67, because the HP67 had more computing power because you could put each of those little magnetic strips, which had 264 bits of memory on it. You could actually put them together and run 10 of those strips. At that level, you had more computer power than we had on the central computer on the airplanes.
that's amazing. So, couple of questions. First, I would like to ask you that what would you like to recommend the graduates, the current graduates or students in industrial, particularly from our country, whether they should take these courses, particularly in, as you mentioned, AI, big data, and how they can drive their career with a parallel with mixing this technology with the industrial techniques in order to drive a better career in the future.
Well, I've been actually thinking about this because I'm thinking about how to restructure all the Six Sigma training that I do in the next year. I'm working with a group of about 30 students from the STEAM and some university professors. And I think what I would do is basically say that there's two fundamental building blocks in analytics today. One is Python and the other is R. R is developed by the statistics community, Python by the computer programming community. So they each have their own strengths and their own weaknesses. I don't really trust Python from a statistical viewpoint, and I don't trust R from a computer viewpoint. So there will be, I think, in 3 to 5 years, and maybe this is something you want to have your engineers do. There will be an alternative to this that merges the two together to a more intensive visualization-based approach to statistics. When I teach statistics, I teach exploratory data analysis, but it's not the one that John Tukey taught. I teach it my way. And what I talk about is a combination of Dorian chain and statistical engineering with the Motorola 4-up charts, and then using eye charts. So the only type of control chart worthwhile learning is an eye chart, because you can take real world data and process it. However, you then have to learn about the distribution that you're processing and create your own rules for when you have a special cause of variation. Because all of the rules that were based in the Western electric system, which came out in 1954, in the Western Electric Quality Control Handbook, those were all based on a normal distribution, because the only control charts that they actually promoted were X bar R and X bar S charts. However, if you get into Kalman filtering, which is the technology in 3 dimensions to replace control charts, paper to be written, Azim.
Yes.
You and you start thinking, what are those pattern recognitions? We see some of the fundamental patterns. We have to have shifts. We have to have some sort of knowledge of trends up, trends down. We have to understand when is variation unusual, excessively unusual. When is the system too tight? It's too locked on. In other words, it doesn't have enough noise in the filter, and now it's no longer able to see change as a result. So it's become insensitive. And when does it get into periods of oscillations? So those are the fundamental patterns that we see. Now the question is, can we create new rules as an adaptive rulemaking system? No longer fixed rules of the past, but let the data suggest the rules. That's an AI system, machine learning, adaptive learning technique you have to bolt onto your Kalman filter.
Yeah.
So that's where we're going. That's where these systems will go in terms of future. Those are things that can be developed by engineers. Great, even doctoral level research projects, I think, and so forth. So that's one of the things we can do. The other thing is how do we integrate the data? A lot of the data that exists and what people are doing, there's a German company called Celonis, Celonis, that's great, well, what they call a process mapping tool. And I just say, nah, all you did was you put a graphical face on RBase 5000's pointer system. So it just tells you there was a logical pointer to an order, and here's where the order went. That ain't technology. That's just, it's drawing. Okay. Now, what technology would do would be to say why the loops occurred.
Right.
So why did it go back? So what was the quality of the reason, and what was the extension, and what could be done about it, and how do we have a learning system so we don't go back to wasted loops? And then how can we prevent that by getting better knowledge at the front end so we can eliminate some of the loops that should be actually made redundant? So again, there's a long way for us to go. So I think people get so enamored with the new technology approaches that they can't see the weaknesses in it. On the other hand, I'm an inherent skeptic. And so I always look at and what does this actually do for me? How will I use it?
All right. Okay, so we have one question from Syed Noor Mustafa Shah. He's probably a professional on Facebook. He says that is quality engineering the domain of industrial engineering, or every field has the subdomain of quality, or is it a separate domain? Who should select quality as a career?
Well, quality is a strange word. It applies to everything. Okay. I can have the quality of love with my wife. You know, that's one quality. I can have the quality of fatherhood with my children. That's a different quality. You know, I can have the quality of my job. That's another quality. So there's a human dimension, a personal dimension of quality. There's a structural dimension of quality where we say we are producing something that is quality, or we have a quality process, or it's a deliverable of quality that's perceived by somebody else, which is subjective. So when we talk about engineering a system for quality or quality engineering, quality engineering, reliability engineering are two subsets of what we call industrial and systems engineering. So basically, we've accepted the merger of industrial and systems engineering pretty much globally now. The American Institute of Industrial Engineers changed its name a few years ago to IISE to embed the systems in to formally recognize what had actually been happening for a long time, that systems engineering and industrial engineering are the same. When I got my engineering credential in Europe, I'm a European engineer in systems engineering and also in industrial. So it's two different communities there. So I ended up getting both because to me it was important that I show that I have demonstrated that competence. So as we look at the future, you know, quality engineering has been a term used by professional quality associations to talk about the people who engineer processes or products to be consistent. Basically, what they mean by this is the system of data management. So it's testing, making sure data systems are good, that we interpret them right, that we control the data through control charting, that we understand the capability of processes, and we can work on improving them through the design of the systems by which we manufacture products. That's basically what quality engineering is doing. Now, I can say industrial engineers do that. So in that sense, it's also a subset of industrial engineering. But industrial engineers do more than just quality engineering. So the quality engineer may not go out and understand new technologies. They may not embed these things. So I believe that the technical components of quality will become more broad as we accept the challenges of these new technologies that are coming to play. I also believe that industrial engineers will be embedding quality more into their work as we start seeing the need to get the systems that we engineer done right. So I'm reminded of sort of a joke about a definition of an engineer, that an engineer is somebody who can make a system more efficient and effective for what somebody else might do for $1, and they can do it for 10 cents. So it's about the useful application at the lowest possible price, and that efficiency component. So we actually measure the money into the systems. Now, to do that more effectively requires another component, and that is financial engineering. I'm totally upset at the way we record finances in companies. Standard costing, which to my chagrin was actually developed by an industrial engineer uh, back in 1917 to manage profit and new product calculations, and all of this idea of burdens and overheads and so forth. All of that distorts the decisions we make about processes because we don't actually look at real costs of systems. We look at a mental model of how we think costs should be done because we're going to take costs I don't know anything about and I'm going to guess or apply them. So basically, most financial systems are lying about truth. And to me, that's unacceptable. That we have to move forward and fix the financial measurement systems. And I think that the accounting community has no motivation to do so because they like established standard work. They want to go make their money from doing these things. But if you take a look at the people who created the financial systems, you'll find out they're all industrial engineers from 1905 till about 1935. And so the accountants back then, they had double entry bookkeeping. They knew they could record the methods and so forth. And it wasn't until McKinsey came along, James McKinsey in 1923-24, that managerial accounting and so forth came into place, and budgeting systems moved the accountants more into the forecasting. And then they had to understand things, but they based it all on the logical of the DuPont analysis methods created at General Motors in the 1930s. That became codified in laws of taxation in America. And then that basically then was set for the world, and we haven't changed anything since then. So in the 1930s, labor was about 60% of the cost. Today, it's maybe 8%. So we still have people worrying about labor productivity. We shouldn't be making decisions on something that's 8% when we start seeing it's supply chain that's running 50% of our costs. So we're making very wrong decisions. And so what I'm going to say is that the historical way of creating quality engineering is obsolete because it's based on the thinking of that quality generation 3. For generation 4, we have to take the advice of Matsui Bashi, who was a 16th century Japanese poet. And he said, don't do what the masters did. Seek what the masters sought. Don't use an Ishikawa diagram. It's stupid. Use a mind map, because the mind map I can actually link into data, and then I could do cross correlations. And maybe if some smart student in Pakistan creates a software application, I can actually then move that right into R or Perl or Python and start using that as a total different system. Whoa. Well, actually, there are some companies doing those things now, but they're not in the commercial marketplace and they're not out there as a normal structure. And these are things I like to challenge the students. Think about how to use the technologies you're learning to integrate what the masters were thinking about. Why did they do these things? Why was QFD so important? It's because they had to build traceability of ideas. The methods, the matrices, that's not what's important. Can we have traceability of ideas? Well, there's lots of ways to do that that are not QFD today if I take a technology solution.
Absolutely right. Okay, so on this note, actually, one question from a personal perspective. In the past 3 to 4 years, what I've tried to do is use open source hardware and technological, technologies. For example, the Arduinos and all of these microcontrollers we have. And the idea is to build low-cost solutions for the SME of Pakistan. How do you see this perspective? Because I've seen other startups also working on this way of building low-cost solutions, automation solutions, and product solutions that could actually contribute in improving the productivity, efficiency, and quality of the SMEs.
So Azim, What I'm going to do is, that's exactly what we need to do.
Okay.
My son is a photographer. He's an artist. And what he does with his classes, he calls these maker marks, and he teaches not STEM, science, technology, engineering, and math. He teaches STEAM, science, technology, engineering, artistic thinking, and math. And what happens if you take some of those devices, which you don't have to be smart at all about to
Yes.
build some of those. You can take them and put them in, and you can start building things together to create a different solution.
Yes.
And that's the maker technology, if you will. Can I build with those building blocks? That's how an SME needs to advance if they want to get into this world. The SME cannot afford major systems. They can't afford all of the engineering to deal with these things. They might be able to afford the one engineer. And I still remember that in 1987, the year he retired from Toyota, Taiichi Ono came to America to give the Toyota Supplier of the Year award at the Fremont factory to a company called North American Tool and Die. The North American Tool and Die, they only had about 120 employees. They made progressive dies. And so they were making sheet metal parts that were actually shipped back to Japan from Oakland, and they were used in the Fremont factory. They only had one engineer. And the engineer was engineering smart, and the people were accepting engineering responsibility at the worker level. So the guy who was making the tools, his nickname was the Hammer, because he would use the hammer to drive those dies together and so forth. But with the engineering technology, they had young people. Jody was the name of the young man who was the quality manager. He was in his early 20s, and he was going to night school. He hadn't even gotten his degree yet. But I remember that when I went there with my son, Andrew, and Jody took my son around. And at the end, the man who was the president of that organization, his name was Tom Malone. If you look up the Tom Peters video, A Passion for Excellence, you'll see the story of North American Tool and Die and Tom Malone on there. And Tom Malone asked my son, he said, well, what did you think about the systems? And my son's comment was, the people love you and they love to work here. And it's because they feel that they can do all of these unusual things. And Tom was taken back because my son was, 7 years old at the time, something like that. And so he said, whoa, wow, out of the mouth of babes comes wisdom. And this is the thing, when we can create this environment where we learn, where we feel challenged, and if we can figure out how do we scope it down to the SMEs. So I spent a lot of time the last 3 years creating a program called Basic Quality or Basic Continual Improvement Specialist Programs for Africa. And we did this program in the Gambia, in Tanzania, in Uganda, in Kenya, one more country, I'm missing it. And so in the East African states. And so the idea was to get the local people so they could then teach it. And I know Pakistan had requested this program to come to Pakistan, but that didn't happen yet. And with this upset of this virus, I'm not exactly sure what's going to happen with the program. But the idea I had was, we took European students from industrial engineering and we're training them to be the instructors in this. We've created video programs, just like I did with the green belts. And we put them up so they're available through the International Trade Center and their website and so forth. And so the question is, how do we actually get the SMEs? The SMEs are 70 to 80% of any nation's economy.
Exactly.
And they are the least prepared to develop advanced state-of-the-art quality systems, productive systems, or even social systems.
Exactly.
So how do we get them so they can understand that? And the answer has to come through some technologically available process that is highly accessible.
Right.
And it's simplified. So using the building blocks of microcontrollers and stuff that you can just buy off the shelf for a few, very, very low cost. Getting these digital sensors and so forth, putting them in place, maybe having that done as a internship of students in local universities. I
Exactly.
think that's the way that we can actually generate some of these capabilities for the future.
And I was actually fortunate to be part of a team with my government organization. You probably know about Small and Medium Enterprise Development Authority, SMEDA, which is the Pakistan organization. And they had a joint collaboration with JICA, the Japan International Cooperation Agency. And they both were actually working in Pakistan, and they went to around 50 local automobile parts manufacturing companies. And I was one of the local consultants who went as a trainee engineer and worked with the local team. We applied various kinds of tools of IE. Always we performed Gamba. We introduced them to Fundoshi and all the different concepts and techniques. And one particular this same point that I mentioned, that they are very eager. They want to get into new technology, but the problem that exists is costly. It's difficult to adapt to. They don't have the resource personnel, the trainings that are needed for their personnel and their workers or their engineers even. So that's where and actually that's where the potential lies. People
Hmm.
usually take problems as it is. They don't see that it's actually an opportunity where, and actually a potential area where people can work. And I have this very crazy idea that if we could somehow educate the SMEs about the open source systems and how their engineers can actually learn from all of the learning opportunities and develop their own solutions, this can actually build a very nice ecosystem where SMEs can actually start building up their own and just start solving their own problems.
Well, that's exactly the motivation why I put the Greenbelt open source technology,
Oh,
because
yeah,
Greenbelt is sort of, I think, the highest level most SMEs need for analytics. We
exactly,
also then
exactly.
have Excel based tools, so you don't have to go to expensive internet systems. So most people buy a computer, Excel comes with it, so you can
Right.
use that for control charts or capability analysis and so forth, box plots. So all of that stuff is in existence today. It's available. You can take a look at the links or on my LinkedIn, so forth. It's had 11,000 views since I put it up there just 3 weeks ago, 4 weeks ago now. Uh, so I put it up on the 1st of May, which is when it went public. And my thinking was that uh, this can go out there as knowledge. Now the question is, who teaches them?
Mm,
And
right.
my answer is students on internships, students doing master's thesis, local universities. They can take that programs, localize that, put it in your own national languages, so that the people can understand the way they need to understand, but that you could have a sound basis. And then when you have small companies in the mountains in Pakistan trying to communicate with BMW, they have the same basis in language and methodology. So maybe they're not building something very big tech, but they're actually providing, maybe it's the dye to go into fabric that goes into a leather. I don't know.
Exactly.
But at that point in time, it's a 20-person company. So how do they communicate around improvement with BMW? Well,
Right.
they'll have a basis because they can actually do that because somebody in Pakistan translates that into their local language, takes the video approach, and then moves it down to something that may be useful there.
Right. Right.
And my reason for doing this is I wanted this in open source. I wanted to have a good process in open source that I could feel I had done a good job in my life. So one of the things as an Islamic person you probably understand is that one of our obligations is to give alms to the poor.
Yes.
So this is
Yes.
my gift to the poor. So yes, you can have a high quality of understanding about these things, and local people, university students, professors can take this and then translate this into their own approach. But I wanted to have it as something that would go out there because there's a lot of garbage on the internet, and I didn't charge for that. Why? Because even though I'm a consultant and I make money from consulting, that's not what I believe is right for society. And so that's sort of the approach. that I was taking. So I agree with you on your approach.
Thank you so much. All right, so it's actually we have been through 2 hours, and my son is here as well now. So thank you so much for your precious time, for your sharing your experience, for this whole lecture. I'm really honored. Really, it's an absolute pleasure to have you, to talk to you. And I would go on with you. We can talk about a lot of different ideas and things and stuff. And
Well, thank you, Azim. And I feel like now I've made up a little bit for having been taken out from our 2013 meeting at your University of Lahore.
yes, yes. All right. So take care, and inshallah, we'll get in touch again. And if you have any further questions, I'll communicate to you via email, and you could respond
That's
to me.
fine. Thank you very much. And God bless you all. May Allah be with you. Inshallah, we'll see you sometime in Pakistan if I can make it.
Inshallah, inshallah. Take care. Bye bye.
Okay. Bye bye.